All right, good morning. We're looking at types of energy today, but first off, you are smart, you are kind, and you are important. Okay? All right, so what we'll be looking at today is types of energy and how we use our energy. It says students will relate information, transformation, and flow of energy within a system. That's part A. When we're looking at how we change, like lighting a match, that would actually be what we call chemical potential energy. And then when we light the match, it turns into light energy and thermal energy because it puts off light and it also puts off heat. All right, and then we'll also here investigate molecular motion as it relates to thermal energy, changing in terms of conduction, convection, and radiation. Main thing we're talking about is how we transfer heat. What's the different ways we can do that? Also, the next one will be determine the heat capacity of a substance using mass, specific heat, and temperature. And what we look at is how much we have to add heat to a substance to raise it 1 degree. And we'll look at that in just a little bit. All right, and also explain the flow of energy and the phase changes through the use of a phase change diagram. So we'll be doing that as well. Okay. So first, let's do this. All right. Types of energy. Okay. Look at that. So, different types of energy we have. One main one is kinetic. And that's just energy in motion. Anytime something's in motion, that is kinetic energy. Okay. Then we have potential. That means it's at rest, it's stored up energy that's not being used. We have chemical, and that is energy stored in bonds. It's a type of potential energy that is stored in bonds, and then when it's broken, when bonds are broken, when things either are cleaved or when a reaction takes place, that chemical energy is turned into kinetic energy. Okay, we have mechanical. That's just the sum of potential and kinetic energy of a system, and that sum will be equal. Let's see what else. We got electrical. Y'all know what electrical energy is. We find that every day. We use it every day. It's powering my lights right now. Elastic. That's energy stored in either some kind of compression or stretching, like a rubber band. That would be elastic energy. Thermal energy, that's heat energy. Gravitational energy, that's just energy stored from gravity. Mainly that's going to be potential energy. We call it GPE. That's gravitational potential energy. Yeah, sorry about that. And then also we have what's called radiant energy. And that's the same thing as light energy. Okay. All right. So kinetic energy is energy in motion. Potential energy is energy that's being stored, not being used, and more specifically, chemical potential energy is when we have energy that's stored in chemical bonds. Mechanical energy is the sum of kinetic and potential energy in the system. We work with that on a worksheet. Electrical energy, anything doing with electricity. Elastic, anything doing with stretching or compression. Thermal energy, anything doing with heat. Gravitational energy is anything doing with gravity and more about how high you're off the ground. And then radiant energy is light. Now, I described these for you. That means you need to write that down somewhere, somehow. Okay? Write that down. All right. Then we have, and we'll talk more about how we transfer that. We'll have a thing we're going to do today. All right. The next one we have is investigate molecular motion as it relates to thermal energy in terms of conduction, convection, and radiation. So, what we look at is the ways we can transfer heat. Okay? Heat energy, thermal energy. There's 3 ways we can do this. First of all, it's conduction, and that is by touch. Example, hand on stove. Okay? Conduction is when you transfer heat from one object to another object when you physically touch that object. Like I said, if you put a hand on your stove and it burns your hand, you're touching that object. Also, we have what's called convection. By liquid, mainly warm to cold and cold to warm. Not necessarily, it don't have to be exactly a liquid, it can be a vapor as well. But when we look at it, this would be like how in summertime your floors, bottom of your floor in your room is going to be cooler than the top of your room. The heat rises and the cool air sinks, and that circulation we call is convection. Some of y'all have convection ovens in y'all's houses that we use for baking. The reason it's so good for baking because it thoroughly cooks the object, because the warm air is rising, cool air is sinking. It's a continuous motion. And also we have radiation, and that's by waves. More specifically, we call them EM waves, which is electromagnetic waves. Okay. All right. And like I said, we'll talk more about this. This is just getting your notes in here. And also this. Next part of our standard says this, that determine the heat capacity of a substance using mass, specific heat, and temperature. All right, so let's look at that. All that is this formula right here. We have Q equals what I'll call MCAT. All right, so Q stands for heat energy. M stands for mass. And C stands for specific heat, which is a given. We'll give you that, unless you have to find that. All right, and then delta T stands for change in temp. More specifically, that's going to be your T final, which is final temperature, minus your initial temperature. Okay. All right, and so we use these things, whatever we give them, and heat energy is always in joules. Everything we have in energy, anything we have. Sorry, my lights went out. Anytime we have anything dealing with energy, either heat energy, electrical energy, anything, that's going to be the unit of joules. You never heard that before, but it's going to be joules. All right, mass we know is always going to be in grams. All right, specific heat is what we call joules per grams Celsius. These are the units we're going to have. And then temperature is going to be in Celsius. Okay? All right, so Q is in joules, mass is in grams, specific heat is in joules per gram Celsius, and then delta T is always going to be in C. And so when we're looking for that, we'll be able to, I'll show you another video of how to work these problems, but just know this, and you need to have these in your notes about what these letters mean and what the units stand for. Okay? And the last thing is this, a phase change diagram. Okay? So in a phase change diagram, what we're looking at, all right, is the amount of energy needed to change the state of an object. Okay? So remember, we have solid, liquids, and gases. First off, right here is what we call our solid phase. And by the way, the phases are these upward lines. All right. And then we have this phase right here, which is our liquid phase. And then we have our gas phase. Okay. All right. And so what happens is that this right here is temperature. All right. And then this line down here is our energy. Now, if you notice, energy is constantly being added. But these flat lines right here is something different, because then in the flat lines, energy keeps being added by our temperature right here that levels out. So temperature does not change in these areas right here. And what we know these areas right here are is a phase change. Okay? And so what happens is when we added heat to a solid, heat energy to a solid, and when eventually that solid is going to turn into a liquid. And what happens is when it's going from a solid to a liquid, it undergoes what we call a phase change. And we represent this by these flat lines on the phase change diagram. And we'll do a lab of this sometime this week. All right, and then once it goes from here to here, from solid to liquid, all right, now this right here is it's a liquid state, and we're adding energy. When it gets to this point right here, it starts to change phase. And once it starts to change phase, the temperature levels off, because we know during a phase change, the temperature is not increased. Okay? And that is a phase change diagram. And what we're looking at is that solids are tightly compacted together, very tightly compacted, like this, for a solid. And then a liquid, they're more spread out. Okay? And then for a gas, they're really spread out. Okay? And let's make sure you write this down about solid, liquids, and gases. Solids have a definite shape and volume. Liquids have a definite shape and a indefinite volume. And all it means, definite means it will not change, and indefinite means it can change. Okay, so the solids will never change their shape or their volume. Liquids will not change. Actually, I wrote that backwards. That's the difference. Indefinite shape and indefinite, sorry, I'm running, trying to be in a hurry, definite volume. Okay, and then we got gases, which is going to have an indefinite volume and shape. I'm probably going to have to reteach this because I'm in a hurry. But all that means is that the volume of a gas can change, and also the shape of a gas can change too. Think about it as a liquid. If you pour liquids into the bottle, the shape conforms to that bottle, but the volume will not change. In the gas, the volume can change and the shape can change. And how can the volume change? Is when we either add pressure or temp. Okay? And if we increase the pressure, we're going to decrease the volume. And if we increase the temperature, we're going to increase the volume. So right here, all right, if we add pressure to a gas, we're going to decrease the volume. Like if you squeeze the bottle, you increase the pressure in a water bottle, and what also is happening, you see the volume goes down. And temperature, if you heat up just say a balloon or something, and the air in the balloon, all right, if you heat it up, the volume is going to expand as well. So we'll be looking at it as well. Okay, that was a very rushed version. Take those notes, and we'll come back and I'll teach to you more as we go along. Okay, take those notes right there, and make sure you got all that, and then I'll work on the thing else I gave you in the Google Classroom. Okay.